So thanks very much for the invitation. Absolutely brilliant to be here. And a perfect setting with the two previous speakers. And I think what we've got to focus on is that if you are looking for treatment for ARDS as a syndrome, you've got to understand something about the pathophysiology and at least focus your treatment on that aspect. So let's have a look. Immunomodulatory therapies for ARDS, where are we? Well, treatments, pharmacological treatments in general for ARDS. We all know that cisatracurium has been published. Laurent Papasan's paper in the New England now a few years ago. Very nice paper, very impressive improvement in outcome, certainly in the sicker patients, so things are going well for that lot. Mechanism, not entirely clear how, but anyway, there's a successful pharmacological treatment for ARDS. What other ones? That's it. It may be because we don't know what we're looking for, it may be the diagnostics, but that's where we are. What else is out there? Well, we're tired of the steroid debates. I won't spend very long on that. Statins. Statins offered quite a lot of promise, but unfortunately, 3 studies, 2 failed, and 1 with harm. So the statins at the moment haven't got any legs to them. Plenty of negative trials. I could have added more to this, but that's what I put there. So what is the future? Well, still a way away, there's things like stem cells, and further away from that, you already heard, there's things that could alter fluid flux, capillary leak, and there's various agents in here that could do that. And closer to fruition is the potential of interferon beta. I'm going to talk to you a little bit about that. And not really on the cards yet, because there's not treatment mechanisms lined up for them, is the other major pathophysiological mechanism of ARDS, which is fibrosis. And we haven't really got something that's working on that front yet. Stem cells, just to say, and you're going to hear more about this, I'm not going to focus very much right now, but you can get mesenchymal stem cells. You put them into a variety of animal models, and there's definitely improvement in those animal models. Probably through secretion of paracrine factors rather than the stem cells themselves growing, proliferating, and remaking the lung epithelium or endothelium. Stem cells are now being tested in thousands of humans in a variety of different conditions: stroke, peripheral vascular disease, acute kidney injury, and there's at least 2 trials getting underway in man. So watch this case. Most of the rest of my talk today, I want to focus on the potential of interferon beta, which is interesting, exciting, and has a pathophysiological relevance. So let's just have a look at what that is. This was the group that we set up that undertook the phase 1-2 study I'll tell you about. But before I tell you about the study, I want to talk about the pathophysiology and the science behind it. What most of us know, ATP is fundamental. It's what makes our muscles move, it's what gives us the energy to drive, to survive. But what we don't often focus on is that in the extracellular fluid, ATP is highly pro-inflammatory. The body knows that, and the body spends quite a lot of time getting rid of it from the extracellular fluid. So it dephosphorylates it to ADP, AMP, and then down to adenosine. And it does that because adenosine is anti-inflammatory. We know in a variety of models, if you raise the adenosine levels, cyclic AMP, anti-inflammatory processes. How does it do this? It uses these 2 enzymes, CD39 and CD73. And of those, CD73 is the key one because it isn't a transmembrane enzyme. It just sits on the surface. It's GPI linked, and the body sheds it. So we can find in serious pro-inflammatory conditions, the body will tend to shed and get rid of, it will shed CD73 and try and replace it, but your levels may be low. That blocks this process, and you dam back up in your extracellular fluid pro-inflammatory ATP, and less adenosine, less inflammation. That's the science, and there's quite a lot behind that. And here's your negative feedback loops. Kofsy did a lot of work on that, where if you get inflammation, you get upregulation of A2A, adenosine 2A on leukocytes. If it's unresolving, you get hypoxia, you get release of adenosine. that binds the receptors, cyclic AMP is released, and then you get inhibition of inflammation. And it's a constructive, virtuous feedback cycle. Plenty of evidence, improved mortality in a variety of models. And if you look in a vascular endothelium, this is really what you've got. Here's your endothelium, very leaky if you've got your adenosine receptor, but very little CD73 and very little adenosine binding. But if you have lots of CD73, lots of adenosine, very little leak. And there's a good scientific evidence for that in multiple species and in a variety of driving inflammatory conditions. More interesting than that is that your interferon beta can upregulate the production of CD73. So hypoxia is on the driving element for the genetic drive of synthesizing CD73, and so is interferon beta. And this is something we're biologically producing ourselves now, but is also a pharmacological agent that can be given to patients. And interferon beta, if it's upregulating CD73, what will that do in a pro-inflammatory condition if you've got a lack of it there? So let's have a look. If you take a standard animal model, ischemia reperfusion, and of the gut, what happens to the lungs? We know that if you get a standard animal model with ischemia reperfusion, you will get lung leak. So it'll get an acute lung injury. But if we give that model, if we give mice in that model interferon beta at the time of reperfusion, so not a pre-treatment, you dramatically reduce the lung leak. So interferon beta can, in that model, significantly reduce lung leak. But I told you that it was working through CD73, and here we can see, now in a slightly more complicated experiment, with wild-type and CD73 knockouts, that if you do a sham operation, there's very little lung leak in the wild-type, a bit more in the knockout. But if you cause lung injury, then more leak. And here, if you cause lung injury, but you add in interferon beta, you dramatically drop your leak in your wild-type, and you don't in your CD73 knockout. So we're now getting to a place saying that interferon beta can reduce lung leak, and it does it through a CD73-based mechanism. So the science is beginning to hold together for the inflammatory part of a lung injury process. That works for mice. What about man? So if you go to human pulmonary endothelial cells and you create a monolayer of them and you injure that monolayer, you will get leak. But if you injure that monolayer and you put interferon beta in, you will significantly reduce that leak. So human cells also will respond to interferon beta. As a pulmonary layer, you will get less leak. But do we in ourselves have the ability to make CD73 in our lungs? We didn't know that until the group got together, took human lung sections, and cultured those in the presence or absence of interferon beta and inflammation. And what you can see here is a significant upregulation of CD73 in the presence of interferon beta, as opposed to the absence of interferon beta. So we now know that human lungs can make CD73, and interferon beta really drives that. That interferon beta is something that can reduce lung leak. So the story starts to come together. But one other bit that's worth noting is that interferon beta has been a treatment for millions of patients. So there's millions of patients right now who receive interferon beta as a treatment. It was the mainstay, not the mainstay now, but was the mainstay for multiple sclerosis. So when you go and look at patients receiving interferon beta for multiple sclerosis, what you also saw is that their CD73 levels went up in the serum. So it's also working in patients. So armed with that, we thought there was a good rationale to try to look at CD73 upregulation through interferon beta in inflammatory ARDS. So we got together this group, and the study we designed, phase 1/2, very simple, open-label study to give interferon beta for 6 days intravenously and try and get a safety and establish a dose. So these were the primary safety, tolerability, establish a basic dose, and exploratory objectives around pharmacodynamics, pharmacokinetics. The study was fairly straightforward. We screened 368 patients at the sites I showed you. We excluded 218 of those patients because we needed to give the drug early. Picking up on the discussion you heard earlier from John and JD, we don't want to be dealing with multiple different pathologies. We don't want to be looking at the fibroproliferative stage of ARDS. We know that it doesn't help then. We've done separate work on that. We want to be looking at the early capillary leak phase. So we wanted to get this drug in the first 48 hours. So if we couldn't get the drug in the first 48 hours, we excluded patients. That left us with 150 patients who were eligible. Now, of those 150 patients who were eligible, we gave the first 3 a very, very low dose. If they were okay, we went up to a higher dose. If they were okay, we went up to a higher dose. And if they were okay, we went up to the highest dose. But mindful of Northwick Park, you will remember Northwick Park, where they gave Tijanero, they gave this pro-inflammatory drug, but they gave it to 6 patients in a row, 5 minutes apart, or 6 subjects in a row because they were volunteers. And then they had a major catastrophe in their hands because all of them became critically ill. So we didn't want to have that. Equally, if we're putting something in that does affect the whole inflammatory process and stop it, we might have late anti-inflammatory effects. So when we recruited our first patient, we put all sites on hold for a month. If that patient was okay, then we opened up to recruit to 3. If all 3 were okay, when we recruited the next one at this dose, we put all sites on hold for a month. So that meant that we had a number of patients who were by protocol not recruited, and we used those as our control. So that was the study, and what did we find? A big and ugly table here. This is in the Lancet paper. Essentially what it's telling you is that our control patients and our ARDS patients had the same basic causes of lung injury. They were basically sepsis, pneumonia, inflammation, and a much lower level of things like pancreatitis and trauma. And it also tells us that our distribution of Apache score and death within Apache score was equally distributed. That just tells us that our processes were working well for a phase 1-2 study. What it did show us, though, which was very interesting, is that we got a biological response from our interferon beta. So if I inject you with interferon beta now, what happens? You don't turn purple or double your heart rate or anything. You just feel a little bit sort of flu-like. So the biological response for interferon beta is something best measured by measuring something called MXA. You can measure other things as well. And when we gave very low dose interferon beta, we got no rise in MXA, no biological response. But as we go 4.4, we got some, and then we got a maximal response to both our 10 and our 22 micrograms. So that was good. We were getting a biological response. And we got a nice rise in CD73. But what we found is, clinically, when we went up to this top cohort here at 22, we had to stop using that cohort because patients had severe and serious Ragors. Indeed, the second patient that stopped us using this cohort had such severe Ragors that they self-extubated from the Ragors. So where we got to is that we could give 10 micrograms, which had no side effects in terms of Ragors, and it got the same biological effect as the 22, and we were getting a nice rise in the marker we're after. So we started to get to quite an exciting place. On top of that, when we measured our cytokines, our pro-inflammatory cytokines were being reduced by interferon beta, but some of our other cytokines were not. So you're getting a biological response in the pro-inflammatory world that we were expecting. What we were not expecting from such a small study was this, that we got a 32% mortality in our control. That was what we did expect. But we didn't expect an 8% mortality in our treatment group. That was very low. And if we looked at the group getting 10 micrograms, which is the optimal tolerated dose at which we expanded on, you can see the same impact. And indeed, that impact happening quite early on whilst the drug was being given. So, in summary, I think we can make the following conclusions. That interferon beta, we reckon we can find and say that there was an optimal tolerated dose of 10 micrograms a day. And that dose was safe and well tolerated. We had almost no observable side effects from giving that drug to any of the patients. I think we had one vascular phlebitis, that was it. That optimal tolerated dose gave the optimal biomarker response, And we measured other biomarkers as well, beta-2 microglobulin, etc., and it did the same with them. It also targeted the gene CD73, and we measured and determined a rise in that CD73. So it was doing what we wanted to do on the tin. It also gave an impressive low all-cause mortality at day 28. So those first 5 are exciting. But we've got to recognize the whole thing we've been hearing about from the last 2 speakers so eloquently. This was a small study. We're targeting a syndrome at this stage, even though we're trying to focus on one aspect of the pathophysiology of the syndrome. So all we can say is it deserves further study. And what have we done? There's a second phase 2 in Japan currently underway, and that has got through its first dosing cohort successfully, indeed very successfully. There's a phase 3 trial being launched now in 7 European countries to be recruiting 300 patients to look at how that goes. The one thing I didn't mention is the impact on kidney and blood pressure, because one of the other things we found when we looked at the patients in the phase 2 trial is that those patients who got interferon beta had a 50% lower number of patients going on to need renal support compared to the controls. And similarly, those patients getting interferon beta had a 50% lower number going on to need vasopressors compared to the control. So there may be more systemic effects other than just the direct lung effects, which is what you'd expect. And there's a major EU grant to look at the role of CD73 as a biomarker. Depends what you're looking at the biomarker of. Here, I think you're looking at the biomarker of capillary leak and the control of capillary leak. So I think you've got to focus down what it's meant to be doing. Does that mean it's an outcome thing? Maybe, but I think we're looking at process. And that's it. Thanks very much.